Welcome to the 10th episode of Weaviate Air. This is super exciting. We finally hit double digits. I have a great crew here with me. So I've got Dirk, Zen, JP, and Philip. So Zen and JP, you already know. Dirk and Philip, they're new to Weaviate Air. So it's super great to have you guys with us. And this is super exciting. So yes, as always, thank you for watching and listening. It's always great to see you all keep coming back for more. And if you like this kind of content, yes, please subscribe, and then you always get a notification. And not just for Weaviate Air, but we do loads of really cool stuff with podcasts and various fun videos, and we also have some more new ideas around tutorials, etc. So it's definitely worth subscribing to our channel. And of course, one of the best things about this kind of content and videos that we are creating, it is live. Therefore, you can ask questions. So don't be shy. Feel free to ask questions always as we go, and we'll try to help them out. But also, if you don't have questions, but you just want to say hi and tell us where you are watching us from, then this is also a good opportunity to introduce yourself to the rest of the community, right? So today we have a few really cool topics to cover. So first off, we will be talking about multimodal models and applications. So Zen will talk about that. The next one, we have AutoCAD feature. So that's something that is brand new that was added to Weaviate with like the 120 release. So JP and Derek will talk about this. Then we have new hybrid search ranking algorithm, and that's also like something that JP and Derek will continue talking about. Then we talk about PQ and rescoring. This is actually a pretty cool topic that Zen will cover. So if you're interested in like various types of maybe indexing and the kind of clever stuff that we do behind the scenes to make Weaviate more performant and more memory savvy even, or to get the best out of your vector database, this is a really cool topic. And then last but not least, we'll have like a really cool demo by JP around like the knowledge base app. So this should be really, really cool. And one more reminder, please subscribe. Like if you arrive late, make sure to subscribe. So and basically, let's have fun during this session. So let's kick it off with Zen. And Zen, what can you tell us about the multimodal models and
Awesome.
applications?
So let me kind of justify why I wanted to talk about this in this episode first. Um, I've been on this hype train of multimodal models recently. I've been reading all the papers in this field. I've been looking at implementations for some of the state of the art multimodal models from Meta, from Carnegie Mellon, and I wrote about this in the previous blog. And I wanted to talk about this as far as how this is going to impact what we're releasing with Weaviate going forward. So let me step back and let's talk about what multimodal models are. Right? Um, the only multimodal model that we have right now in Weaviate is the clip model, and it's multimodal because it understands multiple modalities of data. Right? You can pass in text, and it will embed it into vectors. You can pass it images, and it's going to embed it into the same vector space. And the whole point of multimodality is that you can actually understand and search data across modalities. So you can give it an image and then obtain images or text. You can give it a text query and you can obtain text or images back. So you can do this cross-modal search. And so this really excited me, and I started exploring new papers around this. And now what people are trying to do is go beyond just text and images. And the motivation here is, of course, as humans, we use all of our modalities to understand a data point. Where if you go to the park and you look at and you see a dog passing by, you can see them not just in images, but the time series of them moving. You can smell them if they're close by enough. You can see, you can hear them. There's all these modalities that go in and into our brain, and that's how we understand a dog. And the power of this is that every modality is adding a specific amount of information. Another example of this is I was recently on the plane flying to Seattle, last month, and I didn't have uh, these the wired headphones. I had the Bluetooth headphones, so I watched the entire movie without listening to it, and I got pretty much all of it. So humans are very good multimodal reasoning engines, where I can show you a movie without giving you the audio behind it, and you'd still understand pretty much all of it because we can fill in the blanks of the missing modality. Um, and so the main thinking behind this is if we want powerful reasoning engines, which these large language models are, we need for them to understand other modalities of data. Right now, they only understand language, and some of them understand image. So, like the new BARD model understands images, but in the future, what we'd like for them to do is understand audio, understand moving time frames, so video, understand maybe even motion. So if you look at your phone, there's a bunch of accelerometers and gyroscopes in here. What if you could give the data from those sensors to a multimodal model and then get it to understand what type of motion the human is performing, running, walking, all sorts of interesting stuff. So I went down this rabbit hole, and then we started reading this paper called Image Bind from Meta, and we're in the process of implementing this into Weaviate, and there's going to be more information soon. But the main idea behind this now is that you can take any type of data, embed it into Weaviate, and the vector space is going to represent all sorts of modalities now. Um, and then you can do cross-modal search. So you could pass in, you could literally talk to your database. Before you could write in text and you would get relevant answers back, but now you could record yourself and your query could be an audio recording. Your query could be a video. Your query could be motion sensors actually as well. So you can take a motion sensor, vectorize that data point, and then retrieve back any of the relevant data points back.
Hey Zen, so on the topic, because I think there's like so many things that you could probably
Yeah.
recognize in terms of modalities. So back in the days when I was doing like way more public speaking, I got this gadget. So it's something that you put on your
I had
arms.
it
Have
all.
you seen it? Have you ever seen it?
Yes,
Yes.
I had the same. Yeah.
So this
So
this oh, you have the same. So this thing actually can like it feels like as your different joints and your bones move inside.
Yeah.
So if I make this gesture, show you some fingers,
all
and I'm
this,
not
right?
gonna show you all.
That
You
movement.
do this,
Yeah.
all that, and that's kind of like one of the modalities. So you could, if I do this, you could kind of translate modality of like, oh yeah, this person is happy or something, right?
Yeah.
If I show this, like, oh, this person is angry. So this could be yet another example of like strange modality, and
Yeah,
so
this is
maybe
so
there's some sort
awesome.
of yeah.
That device, by the way, is from a company in Canada, and it recognizes muscular activity in your
Yes.
arm, and this is similar to what the people at Meta are doing with their image bind model. One of the modalities that they process
Um,
is accelerometer data. Right?
and did Meta not buy these? Had bought these startup? So because there was a time where Meta was super interested in these special input devices, and there were a lot of buzz around these, so that they take over. I'm not sure if it was this startup, but at least they to get a replacement for mice, so for a computer mouse.
Yeah, I'm not sure if they bought this one, but I know this particular device that Sebastian is wearing. Um, Yeah, but they are looking at the new interface, right? The whole play around the VR, they want to
Yeah.
be the next screen. Um, no, but this could potentially be one of the modalities, right? If I'm moving my arm like this or like this, what is the closest thing in vector space to this movement action?
Yeah, and I really liked your example in your blog post. So around this infant, which is then growing
Yeah,
up and getting a higher level of abstraction, and then being so like fine tuning or having a model which is then generalizing better. So if you
yeah.
have more data.
Yeah, the other thing that's really interesting about this is that you can do better classification if you have multiple modalities,
Yes,
right?
exactly.
Because
That was the point.
yeah, like if I show you a really weird image, you can only inspect the weirdness or the anomaly component of that image through the image modality. But if I show you a really weird data point through six different modalities, you can view it from different modalities and say, okay, it's abnormal in these modalities, but it's normal in the other modalities. So you can do anomaly detection much better across modalities, which is why humans, like if something seems really weird, like you get a weird feeling, you can't explain it. It might be that all the other modalities are normal. One modality is going off the charts, right? So the number of applications you can do with this is really amazing. I'm really excited to see what people do with this. And one of the main modules, the clip module, people love. So I'm hoping they can take this new image bind module and build on top of it. One more technical detail, by the way. So in image bind, they actually start off with the clip module, and they use the clip module to localize and bring together all of the other modalities. So if you have an image of a lion and the word lion, in the clip module, in the clip data model, those two vectors are already going to be closer together. And now if you project in the sound of a lion roaring, they use examples that are similar versus dissimilar to bind the embedding space together across these modalities. That's why it's called image bind, because they're using concepts of images to bind the other modalities closer together. So hopefully the idea is that you could still use the bind model if you're only doing image and word search, and that would work just as well. But if you wanted to do audio search down the road, going with the bind rather than the clip model would just be a better idea now.
Cool. So you can
go on.
I was going to say, so then from from a Weaviate user perspective, you can now, is it correct to say that you can now kind of embed information or like vectorize information in any of the N modalities this model would support? Like you can have up to N different modalities in your data point, right?
Yeah. If you have the modality, if you have the data point for that modality, which is one of the main challenges of this space. Philip, go ahead. You were saying.
But it's limited to 10 modalities, or?
No, this one has 6 modalities. So it has image, audio, it has accelerometer, it has depth, and it has video, and it's got heat radar. So
okay, because the high modality multi-transformer that has
the high MMT from Carnegie Mellon that has 10 different modalities. That one is super interesting as well. The difference between these two is that this model the bind model builds a model per modality. So you have a model that understands vision, a model that understands audio, and then they bind them together. The high MMT one is one model that they can keep on adding modalities to, and the more modalities you add, it looks at what incremental information you're giving to the model, and it says, okay, this is a useful modality because now I know something that I didn't from the other modalities that I had. And so that builds one model up, and it's a lot more scalable.
Cool. So it's like a Voltron of all the models. Nice.
Exactly. The more modalities you give it, the better it becomes, and you can give it all sorts of modalities. They went into like structured document understanding that model can understand, like Word documents as well.
So what are the use cases that you think we could do with like maybe database? Because like the thing I can think of is like, hey, if I were to vectorize maybe a video, and then I could do either search based on what I can see in the images, just like you were saying, you could watch a movie without even like putting headphones on, or I could just search based on audio, right? So let's say I search for a fight scene, and then maybe you could see it, or maybe there's just a fight that you can overhear, right? So it's always kind of interesting. But what would be other examples you want to use it for?
I think probably the most relevant application would be performing searches. Let's say you have a data point that you have 3 different modalities for, right? You have text for a modality, you have video for a modality, as well as the audio for that modality, which if you take any YouTube video, you have all these 3 modalities. You have the transcription, you have the video itself, as well as the frames, and you have the sound recording for this. You could vectorize all 3 of these data points as separate queries, and then you could do more refined search. Before you could say, okay, show me anything that looks like this image. Now you could say, I have this image or video represented as 3 different modalities. Show me a more accurate representation of what this is in multimodal space. I think that would be one really cool application. The other application could also be if you only have one modality, you can look for other modalities as output from your vector database if you have a large enough data set. This was one of the challenges that they talked about in the paper, where it's very difficult to find rich multimodal data sets How likely is it that you have the picture of a lion, the sound of a lion, and then the motion of a lion in accelerometer data? It's quite rare. So training this thing was a bit of a nightmare. I think they used 7 or 8 different data sets that they stitched together to even train this thing to begin with.
Because I think that the use case in this case wouldn't necessarily even have to be where I have a video and I abstract 3 modalities from it. What you could do is like have a collection where you just throw all my videos, all my MP3s, and all my pictures and all my PDFs, and then I can search through all of them, because that's like the ML model can understand all of them. So I don't have to have 5 different collections. I could actually just lump it in. It's like just search through my unstructured data, right? Like it's all there.
Yeah, exactly.
Cool. Did I hijack you? Did I hijack your train of thoughts?
Oh no, I'm good. Any other questions? We can take those
When
up.
can we have it?
That's we're aiming for the next release, but no promises yet, right? We're just going through finalizing it, testing it. Well, there will be another blog post around all the cool things that you can do with it. All sorts of multimodal searches. I'm really excited about that. But yeah, the next release is
Cool.
we're aiming for that. But
So it sounds like if someone mashed a subscribe button on the YouTube channel, they'll probably get some notifications about videos or content about it in the future.
that will for sure happen. And if you do subscribe, you might it might come out earlier. No promises, but that might just happen.
It's a good excuse to give another call out. And then before we switch topics, we have somebody saying hi from Colombia, which is Codigo. So that's good to see people always saying hi, we hope you enjoyed. If you have any questions, drop us a question, or just, keep saying hi or send us encouragement so that we keep going.
Very cool. Such a wide audience from all over the place.
I know. It's nice to see people from everywhere. Perfect. In this case, might be a good moment to go to AutoCAD feature. So I will leave you, Dirk and JP, to handle it.
Cool. I mean, the last release was so jam-packed with features, right? So we talked about it last podcast with Etienne, and he's been on Connor's podcast to talk about it as well. But yeah, we didn't have time to cover some of the other features, so it would be a good time. And one of them was AutoCAD. And we've got Derek here from the core team. Is that the right group term?
That's right.
And so Dirk and I worked together to write about it. So I thought I'd lean on Dirk to answer all the hard questions, like, hey, what is AutoCAD? Can you just tell us a little bit of, like, at a very high level, Dirk, about what it is?
So you do a search, you get results back, and then they often get bad after a while. So you have 1, 2, 3 good results, and then a bunch that don't have good scores, that are not really relevant to your search, and you don't really want to show them to your users. And obviously you could play around with the limit to try to only include the ones that you really want to show and not include the irrelevant ones, but it's not really possible to set the limit to a value that works everywhere. So what AutoCAD is doing is it depends jumps in the score. So you have, let's say 1, 0.9, 0.85, and then the scores go down to 0.5, 0.4, and so on. And then you do a cut at that jump in the scores and throw away the rest of the results and only show the good ones. And you can set how many of the jumps you want to do, and only include those that you want. So maybe for your use case, you want to go for the second jump or the third to get everything that might be relevant, or you want to really do a hard cutoff and only show the best ones, and then you use one.
Yeah, I think it's really cool because, like, obviously, vector search working on similarity, you have to specify some sort of threshold to get results back, whether it's just, hey, get me 10 results or results within this distance from my query. And that's a little bit painful sometimes because you have to figure out what your threshold is. And what I really find interesting about AutoCAD is that you kind of, there's natural groupings too, as well as like thresholds. You can go, hey, give me 2, like you said, groups of results that are like, because they end up being not necessarily close together, but they're going to become natural groupings of this first group is within this threshold, and then you kind of get this outer ring of results, and then so on as you go. It kind of does this nice mapping of vector distances. So yeah, I think it's really cool, and hopefully our users kind of find it useful as well. Because for me, when I do demos and people are like, "Oh, I see you're getting 8 results back or 3 results back. Why did you do that?" And I go, because that's how many fit on my screen is usually the answer for demos. But it's really hard question to answer when people say things like, "Oh, what threshold should I use if they're using a distance number?" And it's like, how long is a piece of string? Whereas I think AutoCut really lends to kind of natural groupings of these results. So that's really cool. And you kind of need result sets that lead to these groupings, right? Like you kind of need some meaningful distances from results, which is why it works well with vector search.
Yes. Basically, you take the distance we get from the vector search or BM25 search, and that's the input to AutoCut. You don't use anything else. And it's really simple inside. So basically, it's a very simple way of calculating derivative, and it uses that to detect the jumps and then cuts off. And other people are talking about using some complex models to do that, and it probably works better for some cases, but it's a very, very cheap way to get useful results, and obviously can always be improved later.
Yeah.
So is the idea then that if I run a search and I get like a couple of great ones, and then I have like a bunch of like good ones, then the good one gets cut off because they're not as good as the great ones. But if I only get good ones, then the good ones will be shown because there's nothing better, right?
Exactly. So it doesn't look at any absolute values. It only looks at.
It's a relative thing, right?
Sorry, say again.
It's a relative thing. So you can define, I want the first or the best ones, and then there's maybe some space between them, and then I want also the second ranking and the third ranking, and I can do a config thing that I want the first pairs or the first 2 pairs.
Exactly. That's how it works.
Yeah,
You mentioned that it
doesn't know how good your scores are. So you get some scores back and you don't know if a 0.8 is great or not great. So it can't do any absolute ranking. You can only look at the relative distances between the different objects and then group them by using these jumps in the scores, and then cuts it off depending on how you configure it.
It's sort of like when you go for a holiday and you're looking for a hotel, and then sometimes if you book in early, there's like loads of great options. So you don't want like the crappy hotels to pop up. But when you're like booking on the day when you're flying, you go like, okay, at least show me the average ones. Don't cut them out, but don't show like the ones where you get murdered.
I'm also taking these tent at the highway.
Yeah. So like beggars can't be choosers, right?
Yeah, I guess because when we were talking about what image to put in the blog, I said, spill out this really obviously the horrible sketch that it was like Weaviate as a robot grabbing you and like some sets of results. So it's like us basically telling Weaviate, hey, get me 1 set of results or 2 sets of results. How good are they? Don't know. Weaviate just goes and grabs them for you as it's convenient. So yeah, nice. The hotel analogy is quite funny, quite good. Sounds like someone who's been on holiday recently.
But also very specific to your role, Sebastian, or like looking for a hotel for the same day.
Well, no. I'm actually a pretty good planner, so like it only happened once in my life when I had to book a hotel on the same day, but that's not a story live on the screen.
Nice. And Dirk, I think that kind of leads in well with our next discussion, which was going to be.
Wait, I have one more question. This is super important. So every time I learn about a new feature, the first thing that I think of is how could I break it, or try to understand it.
Such a troublemaker, Zen.
So, you talked about using the derivative. Is there a minimum threshold to the derivative? Let's say I ask for 10 answers back, and they're all great. So the derivative is not going to be very high, right? It's going to be a relatively flat derivative. And I ask for 1 cut. Will it just make an arbitrary cut somewhere, or how do we handle that?
No. Basically, if your scores are very linear and there is no jump in them, then it will not cut off anything. It can also be if your results are all bad, but equally bad, then it will also not detect.
Okay, so there is some minimum threshold for the derivative needs to be that high for the cut to happen.
Not an absolute threshold. It detects that the derivative changes.
Okay.
I think it's called the knee in English. I'm actually not 100% sure, but it's a very fast but kind of crude way of calculating it. Yeah, but it basically, if you don't have jumps that are large in your data set, it doesn't really do anything. It can't really group them if they're on a line or something. It doesn't make sense to say, this is the first group, this is the second group.
Okay, makes sense. Awesome. JP, now you can move on. Oh, Philip.
Thanks.
Philip has a question.
Yes.
No, that's a really good question. And to that point, right, about how those groupings are derived, that's led to a change in the, I always get this term wrong, so hybrid fusion ranking algorithm. Did I get that right, Dirk?
Without the ranking.
No.
It's the hybrid fusion.
So close.
Philip, you want to say something?
Nope. I just want to ask, because fusion, the word fusion. But I'm pretty sure you elaborate on it. So relative score fusion.
Yeah. Do you just want to share my screen, Sebastian?
There you go.
Yeah, so this is a picture from the blog post, and this is how hybrid search works. So for hybrid search, we're doing a vector search and a BM25 search, and each of them have their own scores. And now we want to combine the results from both different searches. Problem is the scores are completely different things, and you can't just add them up. It just doesn't make any sense because they measure different things. For vector search, you get distances, and for BM25 search, you get something out of a formula which measures like the frequency of your term and how many documents you have and average lengths and a bunch of other things that go in there. So you can't just add them up. And the method we used before to add the results up just looked on the rank of each result in the individual search and then used the rank to fuse the results. That's why it's called fusion. And the old algorithm was called ranked fusion. And just to kind of show how it works, this is a very simple notebook, very hacked together, so don't look at my code too much. But what ranked fusion does, it looks at the rank in your search results and then assigns a score to it. So the first result in this is the actual formula for it. So the first result in your search gets the score 1 divided by 0.60 plus 1, which happens to be 0.01, blah, 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 blah. Doesn't really matter. The second one gets a bit less, the third one gets a bit less. It doesn't matter what the scores actually are, only the rank counts. And you do this for your two searches, and then you just add the numbers up, and that's your final score you get in the output. And just to show you what that means, so here are two different input scores. Here in the first one, you have a really good one, another really good one, and then a bad one. While in the second one, you have a really good one, and then two bad ones, right? These are crap, and these ones are really good. But both lead to the same results with ranked fusion, because this is the first rank, this is the second rank, this is the third rank, and nothing else matters. I printed out here below what the ranked fusion scores would be for these two scores, and it's exactly the same. And now to compare the old way of fusing things with the new one, I made a small example here. But before I go into that, I just want to explain how I do it now. Or maybe first the problem. So the problem is with this, you get very regular scores out of your fusion algorithm. And if you have very regular scores, you don't have any jumps in your scores. And so AutoCAD doesn't work. And this is what we just discussed. It's not exactly linear, but it's very close to being linear. And so the AutoCAD algorithm cannot find a jump in these scores. And so it will mostly give everything back and maybe cut something off at the end. That has a really low rank in both searches. And now what new algorithm is doing is it normalizes the scores between 0 and 1. So you get your scores from BM25, your scores from the vector search, and you just say the highest score is 1, the lowest one is 0, and everything will be normalized in between according to the relative distances between them. So if we scroll down to these examples, so here the The highest score is 500. The lowest one is 0.09. So this one will become 1. This one will become 0. And the other ones relative to that. So this will be a really low number and so on. For the vector search, this will become a 1. This will become a 0. And because this is so close to the maximum score, this will become like a 0.9, whatever. It doesn't really matter in detail. And what you have with that is the relative distances in your scores from the individual search are then in your end scores. Now, with rank fusion, you only have the rank in the final score. Everything else gets lost. So you don't know if a result was almost as good as the first one or almost as bad as the worst one. You only look at the rank. And with the new one, you have like the relative, distribution of the scores also in your final result. What's important is what you don't have. You still don't know if 500 here is a good one. You know, this could be your best score you get, but it could still be really bad. You don't know if 500 is a good score and a bad score. And now we can kind of, with this made up example, so the first document has 500, second one 4.6, and so on, and vector score is also, second document has a 6, fourth document is a 5.98. I just want to show the outcome for both algorithms. So here we do it for rank fusion. So we just look at the rank of each document, we sum up the score for the given rank, and this is what you get in the end. You see the second one is the best one, and then you have the other ones very close together, and only the one that was worse in both searches is at the end. But if you look at the input, the first one was so much better in the keyword search than the other ones. And here it's on the fourth rank, but the scores are almost the same. So it's still a really good result here, but you only get it on second place. Now, if you go to the relative score fusion, the one is the first result, right? Because it gets a really high score from the vector search and from the keyword search. And so if you sum it up, you get a really high score together. So it's the first result you get back from the vector search. Then you have this group here that has almost the same score. And here is the one that was bad in both searches. And if you would run AutoCut here, you would get a cut here and one here, and you get these groups of very good results, really bad results, depending on what you want.
That's really cool. So I guess it retains a lot more of that information in the scores, right? Like before, all that was kind of like getting lost because all we kept were the rankings, and what we ended up getting in the hybrid score was either, I kind of found that if it scored well in one or the other searches, you tend to come up to the top. Whereas here, how far you are, I mean, because it's still relative, so the top results still tend to do really well. But it was if your second result and you're very far away from that top result, you don't benefit from that as much.
Yeah, exactly. Yeah, I think this jump in the scores is probably the best way to see it. So I could change that to 5, and you wouldn't see any change here. Oops, sorry, I need to rerun everything. It looks exactly the same as before, right? This score is now much lower, but the rank fusion is still exactly the same. Whereas when I would do the same one here, you suddenly get a completely different result, because now this score is almost the same as those two.
But again, now you'd get all of those first groupings of results probably in your one group AutoCut.
Yeah, exactly.
Yeah, that's really neat. So what are the two ranked fusion hybrid fusion methods called again?
One is called rank fusion and one is called relative score fusion. And you can set it with the Python client. In the hybrid search, there's an argument fusion type, and there's just an enum you can import and then set it to relative score or to ranked. And that's how it works. And just for GraphQL, it's the same fusion type, and then you put in one of the two options in. Rank fusion is the default, so the old one. We might change it in the future, and we would be very happy to hear if your results get better. Like what we tested got better with the new fusion algorithm, but it would be great to hear from more people.
Yeah, I saw that when we ran some benchmarks internally, there was some, like much improved recall results with hybrid search. It was really cool. And it's obviously it doesn't, like, it's still compatible with not setting the result because of the default. So if you don't change anything, it should still behave as it did before. So that's obviously neat as well for people.
I have a question. In the example here in the Jupyter notebook, the alpha is 0.5. So both the dense and the sparse search are equally weighted in this example, correct?
Yes.
If I change that weighting, does the reweighting work better with this relative search as opposed to the older search we had?
I think it's more or less exactly the same. So basically you would have a 0.5 or something, or a 0.7 here and here, and for the relative here and here. But the base of it is exactly the same. You still only look at the ranked for rank fusion, and you still look at the relative scores for the new one.
Okay. And then is there any reason why I would not want to use this versus the older algorithm?
I guess we just wanted to get some feedback. For now, everything that we have tested is better, but you never know, right? So it would be great if people say, yes, it's better for us, and then we switch it on for everyone.
Zane is just creeping its way to how to break it.
I'm just thinking about this. Just seems like an overall better thing. It retains more information. Like it just seems all good. I'm wondering if there's anything bad about this, but apparently, so like you said, the testing we've done, it doesn't seem that way. But this is why the community can use it and tell us, and we'll go from there, I guess.
Exactly. Yeah.
Sometimes there's stuff you haven't thought of, so it's always
all the time.
Cool. Thanks, Dirk. Yeah, I think that was really cool, and it was cool for me to sort of be like, writing up about it, and yeah, everything kind of you said as you were showing me this stuff was like, oh, this is like X amount better, and this is X amount better. So everything seemed really positive when you guys were developing it and implementing it. So obviously, if anyone has experiences, we'd love to hear about it. Because I guess one of the questions I had for you, Dirk, was the same as Zen's, like, when would you use one algorithm versus the other? And at the moment, it kind of seems like generally we're kind of keeping the old one for legacy reasons as default, but maybe we'll think about moving towards this in the future. Is that right?
Yeah, if we get good feedback and nobody complains that scores, the results are much worse, then we will switch it over.
Sounds good. Cool. Thanks very much.
So how can I start using it? What do I need to do?
You just, if you use the Python client, that's what you add.
Cool.
And just go to the documentation, check for Fusion ranking methods, and then there are examples for Python, TypeScript, and GraphQL. Oh, it's missing here, but it's already implemented, so it's also hybrid.
We'll add the example, yeah. And is there a way to make it a default, even outside of the query, where it's like, hey, I like it, I want it everywhere, or do we just have to use the flag every time?
You just have to set it right now for each search.
Okay, sounds good. Cool. So let's see if Zen can break it before the next Weaviate Air.
Well, it's good that if I break it, then we fix it, and then so this type of thinking on the limits not just helps with understanding, but also good product. So
absolutely. In the past, I worked with this guy Frank, and he was the torment of all the engineers, because whenever we release like a new product, like a new version of the product, he always found like this obscure example on how to break it. So we always had to kind of like do pre-Frank release and then post-Frank release. That was pretty fun. And no matter how much the QA team tested the tools, like Frank always found something. So maybe Zen, you're the new Frank.
Yeah, sounds good to me.
Cool. All right, should we move on to PQ and risk scoring, because that sounds like it's along the similar subject. So Zen, what is this all about, and how did we get to here? And give us a story.
Yeah, so let me start off with I'll give a quick intro to what PQ is before I talk about the rescoring part that we added with this 1.20 release. So I think it was 1.8 1.18 when we initially released PQ, which stands for product quantization. And the main motivation behind this was now when you take your unstructured data and you vectorize it, all of that, so the huge vectors are stored in memory, and that increases a lot of the memory load, the requirements of what your computer needs to be able to run Weaviate. So product quantization basically says, for all the vectors that you're storing, I'm going to, in memory, store a compressed version of them, and I'm going to have the original representation of them in disk. And the way that it works is it'll take your vector and it will chunk it up into smaller pieces. And for every piece, let's say you have a vector that's 100 numbers long, 100 units, 100 dimensional, it'll chunk it up into units that are 5 numbers, 5 numbers, 5 numbers. And so you've got a bunch of these kind of vector chunks now. And then it trains an algorithm to say, what are the average representations of the first chunk of all of your vectors? It'll take the second chunk and it'll say, what is the average representation of these vectors? And you can increase that by saying, okay, I want 10 average representations for the second chunk, the third chunk, the fourth chunk. So another way to think about it is, if you take a huge vector, it's almost like specifying a person's location down to the X, Y, Z coordinates everywhere. So if I wanted to know exactly where Sebastian is right now, I would give the X, Y, Z coordinate in wherever he is in Europe, and then that would be my vector representation for Sebastian. But what PQ does is it gives you a more coarser representation. So we can say, okay, I don't really care about what X, Y, Z coordinate Sebastian is in. I only want to know what his home address is, or which country he's in, or what continent he's in. So you can keep on zooming out further, but you see the problem now is the farther you zoom out, the less precise of a representation you have for every vector. So with product quantization, you can take an exact vector and you can say, I don't really care about exactly the coordinates of this vector. I'll look at some average representations of this vector, the different chunks of this vector. And so for that compression, you lose accuracy, you lose recall, because now the vectors are not exactly precise. But the advantage of this is you can save a lot on RAM. You require less memory to store all of these vectors. So this is one of the features that we implemented in 1.18, and we've been playing around with it. Users have been using this. Usually how this works in practice is you need a specific number of vectors already in Weaviate, and then you can say, use the vectors that are there to approximate what the distribution of vectors looks like. And then any new vector coming in can then be compressed real time. Right? So there was a portion where I would put in 100,000 vectors into Weaviate, and then I would enable product quantization, and then it would go into read-only mode, and it would calculate averages of these vectors. And then when it came out of read-only mode, the next time I put a vector in, it would compress that vector, and it would have the real representation of that vector on disk, but only a compressed representation in working memory. And depending on how much you compress and squeeze the vectors, you can 1/10 the memory requirements, or 1/100th the memory requirement. The more you compress it, obviously, the more recall and accuracy you're going to lose. But now that's a knob that you have control over. If you value recall, then you don't compress as much, or you don't compress at all. If you want speed, then you can actually if you want less memory requirements, if you have less RAM, then you can crank up how much you're compressing, and you'll be able to store more vectors. So that's the story of everything that happened till now. And one of the problems with the previous implementation was that we realized that there was this trade-off. The more you compressed, the more loss of recall you would have, right? Because the vectors are not more accurate anymore. If I tell you that Sebastian is in this continent, it's harder for you to locate exactly where he is, right? And if JP is also in the same continent, then you can't differentiate between them. That was the main problem. So that was the story up until 1.20. If you share your screen, if you share my screen now, Sebastian, I can talk about the modifications that we've made to improve PQ. Okay, So there's a couple of improvements that we've made here. The first improvement that we've made. Oh, wait, before I talk about the improvements, any questions about PQ? Any thoughts there, guys? Nope. Okay.
This
Awesome.
sounds good to me so far. Yeah.
Okay. So one of the main changes that we made here was, well, we did some memory management to make sure that you can query compressed vectors faster. These are details that I'm not gonna cover. You can read more about these. The first thing that I want to get to is fit time on large data sets. So in my explanation, I mentioned that you need to have a specific number of vectors already in Weaviate before you can enable PQ, because the average representations of vectors are learned from vectors that you already have in Weaviate. So before we recommended that you have 10,000, 100,000, 200,000 vectors preloaded, and then you enable PQ to learn the average representations of the vectors that you can then compress those vectors with and new vectors with. And what we realized was people would put in a lot of vectors and then they would enable PQ, and their Weaviate instance would go into read-only mode for a really long time. So now what we've done is we've added this hyperparameter, the training limit, which says you can set this limit, but it defaults to 100,000, meaning that if you have 1 million or 10 million vectors already in Weaviate and you enable PQ, not all 10 million will be used to fit the PQ algorithm. Only 100,000 will be used. So the time that you have the Weaviate instance in read-only mode is only going to be capped by however long it takes to fit it on 100,000 data points, 100,000 vectors. So this is a pretty good kind of quality of life improvement. The only, I guess, 100,000 vectors is enough to understand the underlying distribution of the vector segments. So this is good enough. If you want more, then you can modify this parameter to 1 million and then or 500,000, and then it'll use 500,000 vectors to learn the PQ compression algorithm.
Zen, are those 100,000 vectors like randomly sampled? Are they like the first 100,000? How does that work?
I believe they're randomly sampled, but I would have to talk to some of the people that implemented it to know, but it would make sense that they're randomly sampled. Because we're only trying to understand the underlying distribution of the vectors, it makes sense to just randomly sample them.
Yeah.
How long does it
Why would
take?
it be any different if it's like
100,000?
first 100,000 versus a random 100,000?
Yeah, so this goes back to the question of sampling bias. Let's say the order in which you pass the data in was really weird, right? Let's say you're passing in images and you're vectorizing the images, and for some reason, let's say you have a grocery store and the first 100,000 objects are all images of products from the vegetable aisle, right, or the fresh produce aisle, and the next 100,000 are images from the cereal aisle or the milk aisle. Now your 100,000 objects are going to be all fresh produce, and so the learned PQ representations are going to be biased towards vegetables. So if you take the first 100,000, your PQ algorithm is going to be all off, as opposed to if you shuffle them and you pass the data in and then you randomly sample from that data, then in that case you'll get maybe, I don't know, 10,000 vegetable vectors, 10,000 milk vectors, 10,000 cereal vectors, and in that case, you have a better approximation of what is found in your vector space.
Oh yeah, that makes sense. Yeah, cool.
Yeah.
And what is involved in that learning? Is it to figure out which maybe parts of like which dimensions are like the biggest differentiators between different vectors? So
Yeah.
if there's like a few fields that are always like between 1 and 0.98, but there's some others that jump a lot, like what's there? What's
Yeah,
going
so
on there?
the main idea behind learning the PQ compression, it's called a code book, because anytime you give me a new vector, I look through the code book to learn what is the vector, what is the compressed representation of this. And so the training essentially takes the vector, cuts it up into a predetermined size, and then it says, I take all of the first segments of all of my 100,000 vectors here, and then I learn what are some good average representations of these. So for example, if we're on this call and we say, I want to learn about, I want to represent people not through their XYZ coordinates, but the continents that they live in, right? Or the countries that they live in, rather. if you only have 2 countries that you can use, it'll take the most numerous country and it'll say, okay, this is a location for an average location for this person. Right? So that's what you're learning approximately. 100,000 works well because it's enough to learn the average distribution. You can also parameterize over how many approximations per segment you want to learn. So for example, if I say I want to learn the average country of this call, and you say I only want 1 country, then that average country is going to be somewhere in between all of our countries. But now if I say, okay, you can learn 3 countries, 3 average countries, then we'll get, I don't know, Germany, we'll get Canada, and we'll get somewhere in Europe, which will be the average of where JP is and where Sebastian is. So those averages are what the algorithm is retaining. Now I don't need to know exactly where JP is and exactly where Sebastian is. I can just remember the average of where you guys are. And every time a new person comes in who's close enough to JP or Sebastian, I'm going to turn their vector into the average vector of where you guys are. And so now you only need to remember a bunch of averages as opposed to exactly the precise coordinates of the vectors. And that's where all the memory saving happens.
Cool.
Yeah.
I have a question.
Yes.
How to break it?
You can break it if you don't allow for enough centroids. So when you fit the algorithm, it's called the k-means algorithm. If you set the k-means, if you set k too low, then it will squish all of the vectors down to 1 centroid, and it will lose all information. So if another answer to that is if you compress too much, then all useful information in the vectors is lost. It's almost like saying all of the vectors now project to 1 data point, and you can't learn anything from that data point. So
And
that's
when I made this decision that I want to then reduce my storage, it's possible to go back? So is it lossless or?
So yeah, that's a good question. Can you uncompress? I'm not sure if you can go back. Dirk, maybe is it? I know there's a way to enable PQ.
But isn't it why we store the full vector on the disk?
Yeah, this is what I was about to say.
You don't have to uncompress. That you have full vector. It's just not in memory.
Yeah,
Okay.
this goes back to the second part of the rescoring component here, because the main reason in 1.18 why you lost a lot of recall was because you're now ranking and comparing distances that are compressed. But now, because we're storing the exact representations of the vectors on disk and not in memory, we can do this rescoring. Whether you can switch back and forth, I'll have to get back. Maybe there's someone in the chat that can answer this. I'll have to look into that, but I think you can. But I want to talk a little bit about this rescoring component, which is the main kind of punchline of the release here. The main idea behind rescoring is, 1 second, I'll talk about it and then I'll show you experiments of before and after. So now what we do is, rather than show you the retrieved vectors based on distance calculation. So if you pass in a query vector, and rather than using the compressed versions of the vectors to return the closest vectors, what we do is you pass in a query vector. We use the compressed representations to learn what are the, let's say, 100 most closest potential vectors. And then once we know the 100 closest vectors out of the millions of vectors that you have in your vector space, what we do is rescore the 100 vectors. We go back into disk and we say, these are the 100 vectors that are the most important. Give me the uncompressed perfect representation of these vectors, and you recalculate all the distances between those uncompressed vectors and the query vector. So now what this enables is, if you had distortions in the ranking of those 100 vectors due to PQ compression, those are completely eliminated, because now I'm rescoring them using the original representation of the vectors. And we're doing experiments around this where before, this is what we had in 1.18, where the more you compressed, the less recall you had, the more distortion you introduced into the system, and the less likely you were to get the correct vector back. So before you were paying a price in terms of recall for your memory savings. But now, because we have this rescoring component, we're running experiments on real world data sets where, if you look at this graph, for example, there's pretty much no difference between the compressed recall and performance versus the uncompressed performance. And this is because when we narrow down on the few vectors that are important, we actually rescore using their uncompressed representation, which makes sense here. The only way that you would lose recall is if, due to the distortion, you weren't able to obtain the 100 best vectors. And so going back to the question of how could this potentially be broken or what could go wrong, if the distortion is so high that the 100 vectors you get are not the right ones, then retrieving the uncompressed version of them wouldn't help that much. But from the experiments that we've done so far, the uncompressed versus the compressed representation is quite basically, you're not paying a price anymore for the compression, so there's no reason not to do it. There's examples of this as well. I'll also show you another couple of graphs here where we took 500,000 vectors of the DBpedia data set, and we vectorized them using the ADA 002 model. So the vectors are 1,500 dimensional, I believe here. And again, you can see the compressed and uncompressed performances. There's no difference because of this rescoring component, which is all important in giving us these results. When we go up to 1 million vectors, you can see that we the throughput, the query per second here, suffers a bit in the compressed representation. We're also running more experiments using the sphere data set. So we're compressing and comparing to the uncompressed representation of 1 million sphere data points, 10 million sphere data points. So we're going to put all of that together into a blog, and then we're going to release it so that if you're planning on using PQ, you can actually look at how much data points you have, what the dimensionality of those data points are, and then what the curve before compression and after compression looks like, so that you can judge for yourself, for your application, what you want to use. But overall, this is all great news, because if you looked at the performance before, there was a material price you were paying for the lower memory, but now for the most part you don't pay a price. So I think the default, you can enable PQ, and then if you see that your throughput is lower or you're suffering on recall, then for your application you might want to do a similar analysis to this, where you look at uncompressed and compressed versions to see for your application if it makes sense or not.
So then basically, if you've got a large enough data set where memory might start to become an issue, that's when you should be looking at PQ, right?
Yeah, exactly. So let me give you a couple more specifics here. So on this graph on the left-hand side, if you look at memory requirements for this guy, the uncompressed vectors, that takes about 5,000 megabytes of memory. The compressed vector takes about 500 megabytes of memory. So the orange line here is 10% the memory requirements, the RAM requirements of the blue line over here, and the performance is almost identical for 1/10 the memory price, which is pretty amazing. On here, the uncompressed version is so this is 1 million of the DBpedia data set. The uncompressed version here is 18% of the the compressed version is 18% memory of the uncompressed version.
So that's pretty impressive, because one of the biggest challenges we've seen, like with vector databases, was like spending a ton of money on having more and more RAM.
Yeah.
But now even like large data sets are affordable for pretty much any business, right? So if before, like you were saying, like, oh yeah, like I have 1 billion, that's going to be expensive. Now you may have 1 billion and you go like, actually, that's okay, I can do it. Or if you have like even 10 million, it's like, yeah. Or maybe you could even run this 100 million in your MacBook or something now, and still be able to get pretty good results, MacBook or whatever machine you're using. So I'm absolutely excited about it. Now I want to run it on my computer and see how far can I push it on my just local machine. until like the whole thing falls apart.
And the great thing about this is that it's all configurable where if you don't care about recall as much, you can keep on compressing. Sure, you'll lose recall at a point, but you can like whatever memory requirements you have, you can compress to a certain degree to fit within those requirements. If you're not compressing too much, you're not paying any price. If you're compressing way too much, then you have to calibrate for what is the price and recall that you're paying there.
Nice.
Hey, and then where can people find all this good info about PQ and improvements in 120?
Yeah, so the blog post is your main go-to. Outside of that, you can go into documentation here. Here we go.
I think there's links below.
Oh, are there links?
Yeah.
1 second. Okay, so if we go here, yeah, these are the two main pages. So if you want to learn more about PQ, so on a conceptual level, some of what we covered here, you can read through this. If you want to learn how to configure PQ, this is available right here, right? So if you go into the vector index config, scroll all the way down to PQ, over here. This is, I've zoomed in quite a bit here, but so you can enable PQ over here. And this is the new hyperparameter that I was talking about. You can set this over here. It defaults to 100,000. So you can read all about configuring as well as the concepts behind this as well. And then small plug here, we're gonna talk all about this in a new blog post that's coming out soon as well.
Nice. And all those links we also have in the description of the video. Or if this one is not there yet, we should definitely add it after the session.
Yeah, it's all in that release blog. So, and there's links to all the documentation pages within each section of the blog, so you can follow through after you read about the feature as to how you configure it, and the conceptual pages that describe what it is at higher level and so on. So, yeah.
Is there like any performance difference in terms of how fast the queries are? Because if we don't have to do like the precise scanning,
yeah,
is
so
that like
you actually pay a price in terms of throughput. So as you can see here, if you have a compressed representation, you can
right.
you can run less queries per second because of the distortion that the compression introduces, and also because of the codebook lookup. Every time you have a vector, you have to look at the codebook, so that takes some time as well. So it adds a little bit of latency, the compression.
So it's almost free, but not quite.
Yeah, you can also tweak the latency, so you can play around based on the parameters of PQ. You can trade off memory with your latency as well as recall. But if you look at the HNSW parameters, you can tweak those for latency versus recall as well, right? So there's a bit of juggling between the parameters between QP and then HNSW going on.
Or maybe the savings you make on RAM, like where spend less money on RAM and then put more powerful CPUs or with more cores, and maybe you could actually recover some of that performance just purely because you have more raw power to do other parts and calculations. So it could be that if you look at it just purely from like financial point of view, you might end up spending similar amount of money or less and yet get like something faster because you move your investments all around, like withdraw investments from RAM, put more into the like a CPU land, and you're doing well.
Portfolio management, huh?
Yeah, you an economist on the plane,
Yeah.
Nice.
All right, awesome. That's all I had to do with PQ and rescoring, folks.
Perfect. Any more questions? Oh, one way to break it would probably be to increase that limit, right, to 10 million back to, and then
that
go
would
to
that
read
would
only for a while.
Yeah, that would move it into read only for a long time, because now it's going to learn the distribution over 10 million vectors. Before we had this limit, if you had put in 10 million vectors in there, that's what it was actually do. Yeah, so that's.
I propose we call it the read only comma.
Yeah.
That would be perfect. Hey, so last but not least, we have the demo from JP. So, JP,
Cool.
do you want to show us your knowledge base app?
Yeah, sounds good. I'll be pretty quick. So, Sebastian, if you can share my screen or at least my
Of
app,
course.
a PyCharm app. So the motivation for this is that I think twofold, right? One is that I run these Weaviate workshops every so often. And quick plug, we've got one coming up tomorrow, 4 p.m. British Standard Time. So if you can join us, find the link maybe on the descriptions, but also on our social channels. And people like really enjoy seeing, practical examples of what you can do with Weaviate, as well as like, sort of like the simple queries that we show in introductory webinars, right? So that was one motivation. The other is that sometimes I get a bit lazy. So like I recently got a PlayStation, and one of the things I wanted to do was like, hey, what games do I get, right? And there's like all these great YouTube videos on like video, game reviews and whatever else, but I don't really want to watch 15 minutes of videos each time I want to like, learn about a game or like a feature or something. And I thought I would put the two things together and build this fairly simple app. So so what I wanted to show here is just kind of like how it's abstracted. So here I'm just instantiating the app, and what it does at a very high level, it creates a Weaviate instance and dumps all this text information that I give it into one collection, right? So I can give it YouTube videos, I can give it like a text file. So this is like some text of what Kubernetes is just from the website. I can add Wikipedia articles just by giving it the title. So these are all kind of wrapper functions for doing things like that. I can even add YouTube videos just by giving it the URL, like so. So this is the release podcast that Connor and Etienne did. And then I can do things with that content, which is like really, really cool. And look, I'll show this in more detail in the workshop, but writing these wrapper functions were really, really simple. So that's why I'll be showing that in the workshop. So here I've got a function to summarize a particular entry. So what I'm doing is summarizing the YouTube video that I imported above. I won't go through a lot of details of what's happening under the hood, but basically what it does is it gets the YouTube video, downloads it, gets the transcript through OpenAI, and then ingest it into this Weaviate database by chunking. And chunking is fairly simple too. And I can go, hey, what's this video about? And it says it's Etienne talking about Weaviate 1.2, and you can learn about all these things like memory usage, shards, multi-tenancy, and so on. So, again, I can get a high level view of this content without like, listening to it. So I can say, decide from this summary what I want to do with the video going forward, right? Or I can go, or actually, maybe not limited to this specific content. I can go, well, based on everything that's in the database, what can I learn about if I give it a particular topic? So if I go, and this is a little bit of prompt engineering on my part under the hood, I can say, well, maybe I want to learn about Weaviate, but I don't know what kind of things I want to learn about. So based on the content that's in the knowledge base, I might learn about hybrid search, module system, blah, blah, blah. And in a similar way, I can just give it a particular prompt and do something with the content. And for example, here I imported a video game review. And this is just, it's quite verbose the way it does things, the particular library. And I can say, oh, what kind of gamers might this particular game appeal to? And I can ask that to this video content, right? So it'll say this game, blah, 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 might appeal to people who enjoy action adventure games with emphasis on storytelling. So it's all, stuff we've seen before in terms of retrieval, augmented generation, right? So that's fairly standard. But and just I wanted to show people just how simple it is and how easy it is to put these types of apps together using Weaviate. I want to write another wrapper function, which I haven't done, is to summarize multiple videos, which I haven't done that, or multiple bits of content. But yeah, that's the really high level summary of what I was trying to build with this app. And I've got even just a fairly simple text search wrapper, so I can just search for a particular phrase and it gets me, whatever number of chunks, right? So if I search for the phrase multi-tenancy, it does a vector search and I get different chunks back, right? So I get like source path, title, and so on. So yeah, that's the app. I'll stop raving on about it. It's really inspired partly by my laziness and not wanting to watch these kind of like, YouTube videos of reviews and something that's potentially a little bit, a little bit long. But for demo purposes as well, because people really seem to enjoy playing with the generative search module, which is really powerful in terms of making your data dynamic and interacting with it. And I think the topic of chunking seems to come a lot too, right? I've got this long piece of text, or I've got this video which can't be fit into one object, and to be honest, you probably don't want to anyway from retrieving information from it. So I wanted to show that as well. So yeah, that's me, and that's the app, and it's not open source just yet. It's on GitHub, but I haven't released it. But I'll do that as well for people to check out in the near future. And if you want to see it as a bit of a preview, come to the workshop tomorrow, and then you can ask me questions about it and then check it out in more detail.
One question or two questions.
Yeah.
Is when you get a transcript from OpenAI, is there also a timestamp included? So it's possible to jump to a specific timestamp in the video where the transcript is?
So I believe you can get timestamps. I haven't set that up. I've seen other people write apps with timestamps. I haven't done it. So all I do is to get the whole transcript through Whisper and chunk that up because no, sorry, I get the YouTube video. I chunk that up because the Whisper API has a limit as to how big the file can be. So I kind of make it certain, like 15-minute segments or something, get transcripts from there, and then they just get chunked based on whatever word limit that I have. So it's like a fairly basic chunking mechanism I've got at the moment with a little bit of overlap. So it's like a sliding window type deal. And all the bits can be swapped out. So I'll be building in like other chunkers and all that stuff. And we should be able to build in timestamps as well, because yeah, it'll be really good to be like, oh, I want to find out the piece, a bit of this video where they talk about like gameplay demos, or like where they talk about performance or whatever it is. Or if I want to look at Etienne's podcast and look through the bits where he talks about the hybrid algorithm, right? So something like that. That'll be really useful for sure.
Yeah, would be super nice to have one single point of truth around documentation. So we're feeding in our docs, the written docs, the YouTube videos, and whatever it is, multimodal documentation or how to use Weaviate, and then having this one single point of entry for people want to learn Weaviate or to understand.
Yeah, I think that'll be cool. And that was one of my other motivations was too, because I want to learn about, if I want to learn about containerization and Kubernetes, right? I can just dump in all this information into it and start asking it questions. And if I kind of get the prompt good enough and kind of careful about looking at the results, hopefully it doesn't hallucinate too much, right? In terms of generating results from the retrieved text. And I think that'll be really cool for sure. And I haven't checked out like getting the language model to produce code, but I'm sure you could do similar things if you give it enough like
it's possible, but then I was part of several projects doing these, because one of the hackathon projects did this, and also at Gina. And one of the problems is that then the dependency, so the model is hallucinating the dependency or the versions of the program. So one of the tricks is then to build a chain. You're handing in the error you're getting, and then doing a next iteration.
Yeah. So yeah, the detail around that gets quite tricky for sure.
I think the tricky part is with maybe false positive. Like, what if we give somebody a piece of code that is just not a good advice or not a good, piece of code, and then they kind of maybe learn the wrong way, or they just go like, "Oh, this is all broken," right? And I think we've all seen it way too often. But yeah, I think this would be cool because we could combine many of the things we talked about today. Because if we use the multimodal models, then we can search across all of those different results, then include AutoCAD to kind of exclude maybe some of the poorer results, right? And then throw in some, PQ, and then reduce the amount of memory, and maybe you could run the vector search on all of the Weaviate documentation and videos directly on your machine, right? You don't even have to have it in the cloud or somewhere, right? And I wonder if we could even shrink it so much that we could put it on a mobile phone, right? And then I could take it, offline, take it on the plane and stuff like that. That would be pretty awesome.
for sure. Yeah.
Let's
Nice,
go.
nice, love it. So we have like some good, nice, warm words from our audience. So Brent says he liked your presentation, JP. So thank you, Brent. We're really happy to have you here. Felix also enjoyed today's sessions, and so he liked our presentations. And of course, we didn't forget about Codigo. I'm not sure if that's actually your name, or maybe this is just like in a different language, like a coder in Go. Maybe, I don't know. I'm gonna claim ignorance right now, but we don't forget you.
But also the avatar is Go, so it could be.
Yeah, but it could be like Sebastian Go. Like, so I don't know if Codigo is a formal name, or maybe now it is, right?
And
my
if your name's
firstborn, I will
Codigo,
name him Codigo.
I was gonna say, if your name is Codigo, you probably have to pick up Go, right? Like you can't be like, oh, I'm a dev, my name's Codigo, Go, and I don't write Go. It just wouldn't work.
I know, right? Like, so you can set up your kids for success or failure depending on what framework you name them with. Yeah, like I have a cousin. His name is AS400. He's not doing well anymore. This is great. This is great. I think that's it. I think this was an amazing session. Thank you all for joining. Thank you for the audience. Just like one final reminder. So thank you for watching. Thank you for listening. And then remember to subscribe, because this way you get a notification from YouTube whenever we do cool stuff. And if you have any questions, even after this, you know where to find us. Just come to the Weaviate community. Definitely find us there. We are there. We're pretty active. And then we are working on all sort of things. But also, if you build something really cool and maybe you'd want to join one of those sessions, we're always open to having cool guests. Or if you have idea on a topic, right? Like, hey, I'd like to see more of this or that. I'm pretty sure we'll do something about LangChain the next time we come around. Because we've heard that this is a popular topic, but maybe there's some other topics you're all interested. So, but yeah, thank you for watching us, and until the next time, yeah, have a great day.
Bye, everybody. Have a
Bye.
great day. Bye.
Bye.